Okay guys, welcome to the photoelectric effect. So Einstein came up with this idea many years ago, a bit over 100 years ago now actually, and he based it on the idea that light wasn't just a wave, or light didn't just behave like a wave, but light was a particle that behaved like a wave. And before him, people used to think about the ether and all this other sort of stuff. And what Einstein wanted to do, because he was a physicist, a scientist, he wanted to prove experimentally that light behaved like a particle. So the photoelectric effect is how he did it. So photons and electricity, or photons and electrons, and one induces the other. So what he started with was the idea of conservation of energy. So the energy into a system, take the energy used, is the energy left over. Alright, pretty simple concept. If you start off with 10 bits of energy that you put in and you use up 3, you'll have 7 left over. In terms of the photoelectric effect though, the energy in, I'll swap colours, the energy in is from the photons. The energy used is the work function of the material itself, and the energy left over is the K max, or Ke max, of the electrons as they exit the metal surface. So Einstein's experiment basically consisted of this. A photon, so we've got a blue one, a green one, and an orange one, because they don't have red. And what they're going to do is shine on this metal surface and interact with the electrons that are somewhere near the surface. Now, with the, start with green, with the green one, it has a certain amount of energy. It's kind of in the middle of Roy G. Biv. So here's green, it has, somewhere in the middle of energy. This end here has more, and the other end up here, so the reddy orangey end, has less. So as we decrease the wavelength, as we're going that way, we increase the frequency, which means that we increase the energy, HF. In terms of this, what we're going to have is a certain amount of energy that it takes to release the electrons out of this metal surface. We call that the work function. If the frequency of this orange one, or this green one, or this blue one isn't high enough, so if basically HF isn't bigger than W, we don't have any Kmax left over whatsoever. Now, we can use blue photons to release energy, or release electrons in this case, and what we might find is that the blue photon has more than enough energy. It's just that it can't give some of its energy to one photon and whatever's left over to another one to kind of help it out. It's all energy goes to a single electron. Alright, this is really important. We can't have some of the energy going to one electron, some of it going to another one. When we get to the X-ray production, you'll actually see it's a little bit different. So all of the energy goes to one electron, and if that energy is enough, this electron will jump out of the surface. Alright, the easiest electrons to get are the ones near the surface. That's where the work function comes in. The work function is the minimum energy to release that electron. If we have more than enough energy, the electron will come out and it'll have leftover kinetic energy, and it'll be moving at a certain speed. If we shine green light on it, and let's say it still has enough energy to let this electron escape, what will happen is there'll be less energy in the same amount used, so we'll have less energy left over. So it might be 8 bits of energy in, still 3 bits used up, and we've only got 5 left over now. If those same photons try and release one of these electrons, it's going to take a lot more work to do so. So not all of the electrons come out with the same amount of kinetic energy. Some of them have lots. The most kinetic energy of the electrons is based on this. All of the others have either the same amount or less. And it just so happens that some of these electrons, so let's say this one down here, might have enough energy to get to about there, and that's about it. All we've done is shine light on it, we've moved that up, it's probably going to now shuffle its way back down, but we've given it some kinetic energy, just not enough to get out of the surface. Seeing as we've given it some kinetic energy, all it's going to do is warm up. Alright, if we ramp up the frequency more, so we go past blue, I don't have anything past blue, what we'll end up doing is increasing the kinetic energy further and further and further and further. All right, if we come back the other way, so we go from blue back down, orangey, red, which is our lowest wavelength, so our longest wavelength, our lowest frequency, our lowest energy, what we're probably going to do is get to a point where this doesn't have enough energy to release any electrons. So what we've got is HF take W, so our K max is HF minus W, and what we're finding is this is less than W. So we don't have enough energy left over, so our maximum kinetic energy is a negative number. That makes no sense, it's nonsense. So that electron, this one here, doesn't reach the surface, it's not emitted. If we change the experiment slightly, so we're using a different colour, yellow or even green, what we might actually find is that this colour does have enough energy to get that electron out. So what we can talk about now is the minimum frequency, or the threshold frequency, which is equal to the work function. So at some point we get to a number here where it's exactly the same as this work function, which means that we're getting electrons to the surface and they're pretty much jumping out, but we need to go a little bit further in order to start giving them some sort of kinetic energy. If we increase the intensity, so we have more photons of light shining in, we're not going to get faster moving electrons out because we haven't changed the frequency of our light, but what we're able to do now is get more electrons come out. So instead of just one per whatever it is, per second or per millisecond or microsecond, we're getting more and more and more. So in changing the intensity doesn't change the amount of energy they have left over, but it does change the number of them that we're actually going to get coming out in the first place. The very last part that I want to talk about is the graph for this part. When Einstein was doing this, he knew that if he had his experiment, so what he's measuring is the maximum kinetic energy of the particle, what he was changing was the frequency. What he noticed was that all of these data points for a specific metal were lining up. And if you look at this thing here, if we look at the dependent variable, the independent variable, the slope of this line should actually be Planck's constant. This point here, where HF is equal to W, so we've actually got it's crossing past the x-axis. There's our F0, and down here is our y-intercept, which is at W. That's our work function. And Einstein was doing this for a series of metals, and he had some reactive ones and some less reactive ones, but he still found they all had the same slope. And all we were doing, or all Einstein was doing, was kind of got the same slope, was changing the metal, so they're all getting different and unique threshold frequencies, which means that they're all getting different and unique work functions down here. So as he was using less reactive materials, so we're moving further this way rather than over here, what he's actually finding is that it takes a higher threshold frequency to release electrons, which means that the electrons in here are bound more tightly to the metal itself.